Start now?
Yes, the recording has been started. So now, yes, I think you can start.
Okay, so last week we saw the basics of semi-definite programming, and today I'm trying to illustrate how do we use semi-definite programming for quantum state discrimination, which is the topic I'm working currently. So let me start by defining what is quantum state discrimination. Imagine that we have a set of quantum states, rho I, and we have from 1 to n different states with given prior probabilities, eta I, of having them. And with this, we can define the ensemble of unnormalized states, eta I times rho I for the states. And once we have one unknown state, we want to make a decision in identifying which of these states we have. For that, we use quantum measurements, POVMs, which are just nothing but semi-definite operators that sum up to the identity. Okay, it's a bunch of operators that fulfill this condition and this other condition. So the picture to have it in mind is, okay, given an ensemble that you know, okay, you define, as we said, we have one of those states with given prior probabilities, but we don't know which one of them it is. So we perform a measurement and obtain an outcome I, and then we make a decision rho I. Okay. So what's the point on considering this? Okay, I think the objective, which is identifying which of the states we have, is clear. But in quantum, we can measure through a lot of measurements, and we want to use the one that maximizes the success probability or minimizes the error, or it depends on the cost function that we are assuming. Okay, but we have the freedom to choose the measurement. So the most typical scenario is the one that is called the minimum error. In this one, we are trying to minimize the error that we have when we are inferring which of the states it was. No. So we can write it in an SDP form, okay, as it is shown in here. So we have to minimize over all possible. Are you? I think. No, it's showing. We have to minimize over all possible POVMs under the to minimize, sorry, the objective function of the sum of the unnormalized states and all POVM elements that don't correspond to the given state. Okay, subject to that the POVM elements fulfill the completeness relation, they have to sum up to the identity, and that they are non-negative. Okay, these are just the constraints of the POVM elements to be a quantum measurement, and we are minimizing this. As you can see, another equivalent formulation, because in here we are considering the error, is to maximize, instead of minimizing the error probability, we are maximizing now over the POVM elements, or the POVMs, to maximize, instead of the error probability, now we are maximizing the success probability. Okay, and in here it's the same. We are summing over all possible unnormalized states with the one now that corresponds exactly to the state. So remember that if we obtain the outcome I, we will infer that it was the state I. Okay, and again, they have to fulfill the constraints that these EIs, these operators, are a POVM. Okay, but this is not the only thing that we can do with SDP. Holevo in the 70s describe a conditions that a POVM have to fulfill in order to be optimal. Okay, so given an ensemble of the way I defined before, a POVM set of operators positive that have the completeness relation is optimal if the following two conditions hold. First of all, that the sum of the operators multiplied with the unnormalized states minus sum of the unnormalized states is greater than 0, and then this expression is equal to 0. And at the beginning, this was formulated or discovered without using SDP at all. But later, independently of Holevo, Yuan and collaborators saw that this is just the formulation of an SDP program, a convex optimization problem. So remember from before that we have that the objective function was this one. So we can start constructing the Lagrangian, and we have the sum of the normalized states with the trace of the operators. And then we have to add the penalties for each one of the conditions. First of all, they have to sum the identity. Okay, and we only have one of these constraints. So we have only one dual variable that it will be permission, if you remember. And that for each one of the POVM elements, for each one of the i's, we have a positive operator set I, which will be the dual variable. So as I explained last week, putting all the primal variables together, okay, we have one constraint for the dual semi-definite program, and the rest that is independent of the primal variables, which will be the objective function of the dual version. So the dual at the end reads easy because it's way easier, the formulation of the dual program than the primal, and this is useful because it will derive new techniques for solving the SDP program, the optimization problem. So the dual reads the minimization of some operator y, the trace of, sorry, I think it's, yes, the operator y, subject to that this constraint here is equal to 0, but remember that Z was a positive operator, so we can impose it in these conditions. So the operator y has to be greater or equal than the unnormalized state rho I for each I. Okay, and more that the operator is Hermitian. Okay, from here, we already have the first level condition. But if we want that the dual objective function has the same output as the primal objective function, we can impose that the y, this dual operator, is equal to just the sum of the multiplication of these hypotheses and elements. Okay? Is it clear here? I hope.
Hello.
Yeah.
Yes.
Iago, in these dual problems, when you are using this eta I rho I less than equal to y.
Yes.
Okay. Can you just explain once again? Because from your earlier notations, your constant was eta I rho I minus y plus z is equal to 0, right?
Yes, that's it.
Okay. Now zi is equal to 0. Now you are saying since zi is greater than 0 always.
Yes, you can. So it is imposed that Z is greater than 0. So you can solve for Zi, and you can say that Zi, is equal to y minus eta I rho I, right?
I see. Okay.
But then Zi is greater than 0, and therefore
yes,
this has to be greater than 0. So this Z is called slack variable, and a lot of times you can just erase it. Not always, but in most of the simpler cases, let's say, and quantum state discrimination, it happens a lot, you can just assume that it's positive and use it for the other conditions, for the other variables to fulfill this positiveness. But you can forget about this one. If not, you will have to add here the set variable. Sorry. Is it like this? Well, you can, I'll write it, space y, and then subject to that y minus eta I rho I is equal to set I. This is Hermitian, and this one, sorry, is positive. So if you cannot see it right, but you will have this one. But you can simplify it a little bit by just assuming that set I is positive and impose it to the other condition, to the other two variables, sorry. Now
Thanks. Thanks.
Okay.
Yes, it's clear. Perfect.
Then, so if we want that the dual problem is, the output of the dual problem is equal to the output of the primal, we have to make that this trace of y is equal to this sum of traces in here. So we can assume that the operator is just simply this object in here and see that they have the same trace. So assuming this, the dual and the primal will have the same value. Also, if we assume a strong duality, we know that this object in here has to be equal to 0. And this is a little bit less clear why, but if you see this condition over here, and you want that these two objects, these two objects are equal, you need this object, all this object, to be equal to 0, right? In order to obtain the same output for the two problems, right? And now, if this sum of traces is equal to 0, each of the traces has to be equal to 0. Why? Because all of these terms are positive. And therefore, only for one I, this trace has to be equal to 0. But because this is positive and this is also positive, the trace of two positive matrices is positive. Okay, and this is easy to see. And then if we want that this is equal to 0 in order to have the same output for the primal than the dual, we need that this condition holds, that this multiplication of matrices is equal to 0, to the 0 matrix. And moreover, if we multiply to the left by some other POVM element, EJ, this is also equal to 0. So at the end, we have this condition for every I and J, and we can use two of them to obtain the second whole level condition. The first one arises from this condition, is the same one, and this one arises from complementary slackness. Okay, so at the end, all problems in, at least for minimum error, well, for all cost functions, but for minimum error is clear, can be described as an SDP formulation. Yes.
Yeah, so when you assume this strong duality, you have put that y is equal to summation over eta I pi ei. How general is this? Like, can there be another possibility, like in a sense that this is one possibility where both the solutions will agree, or so your duality gap will be 0?
No, but you can have.
Are there other possibilities also?
It could be some other possibilities. It depends how degenerated the solution is.
Okay.
Okay,
so like
but in principle, you are assuming here that y is equal to this operator. Okay, just to have the same traces in the primal and in the dual. You're assuming it. And if the rest of the conditions are fulfilled, then you are sure that this is the optimal.
Yes.
But it could be that there are some other solutions. For example, in zero error, we'll see later, I've encountered some problems that have more than one solution. And also, EI, it depends on the problem, but it could be for qubits. For example, if you have 5 qubits to distinguish between, your solution is degenerated. And you can have Y equal to this sum with this EI, and these EIs can be a collection. It is not unique, the choice of the measurement.
Yeah. So this Holevo condition, it's the sufficient condition, right? That is what you're saying? Okay. So this can be derived through this way also, but there can be other solutions which can still give you optimal POVM, but they might not satisfy Holevo condition.
No. If a POVM is optimal, it satisfies Holevo conditions.
Oh, okay.
Yeah, in here I derive the sufficient part, but it's also necessary.
Okay.
But I think it's illustrative to do it in this way, to construct it via the semi-definite programming. But if you see these two papers, it's sufficient and necessary. So all optimal POVMs fulfill the Holevo conditions.
Okay.
And I want to mention, to not be confused, that this Holevo condition, the first one at least, is is for the minimum error scenario. Okay, if it was not the minimum error scenario, in here it would be another factors involved. Okay, but for the minimum error, it has this simple form, and is the one that it's most common or known, at least.
Okay, thank you.
Okay.
Iago,
yes.
So the Zi finally turns out to be 0 for all I under the strong duality assumption, no?
Yes.
Because, yeah. Okay.
When we go to the 0 error case, sometimes Zi has to be something. And it turns out that I know a couple of instances that Zi has to be some projector. It's not super common, and I have not encountered it in minimum error, at least. But sometimes you can forget about the slack variables, but the initial problem, and the important to keep in mind, is this one. Sorry, is this one.
Yes.
But in most of the cases, you can simplify it. In most of the cases, but sometimes you need something else.
Okay.
Okay. So let me go to another instance of state discrimination, which instead of being the minimum error scenario, now it is the 0 error. And what is that? That we allow no error when making the decision. Before we were minimizing the error in order to maximize the success probability, but in here we are fixing the error to be 0. We cannot say it was an hypothesis 1 if it is the number 2. We have to be sure, if we are saying something, we have to be sure that this something we are saying, this hypothesis, this output, is true, 100%. Okay, but of course this comes with a penalty. Okay, that we need an extra outcome that is, well, I don't know, I won't make any decision because I have no information enough to be 100% sure. Okay, so in here, now the maximization, it's again on the POVM elements, and it has the same form as the maximization before, but now we are having, instead of 2, 3 constraints, that they are positive, and added that they have to be 0 when tracing with the operators that corresponds to different outcomes. Here you can see J and I. So if I obtain, it's impossible, sorry, to obtain 2 if it was the number 1 hypothesis. And the sum over I has to be less than the identity, less or equal. Okay, why? Because we are adding a new POVM element. Okay, so if we add here, let's say this, I don't know, element, it will be equal to the identity. Okay, but this sorry, this the dual of this one is a little bit more complicated.
Sorry,
Yes, sorry.
Yeah. So how the positivity of E question marks is assuring here?
Because it has to be a P of M, right?
Yes.
So is equal to the sum over I of all elements plus, right?
Yes.
So identity minus the sum of all i's, yes,
Yes.
is equal to 0 from here.
Yeah, but what I'm asking, you have, I mean, how are you? So in your EI, E question marks is also defined, right?
I'm sorry, come again.
So where are you defining the positivity of E questions? I mean, because all of your EI are not
Yes,
equal with E questions marks. So E questions marks is something else, right?
I'm sorry,
Then
I'm not getting some word. All of EI's are equal to what? Sorry.
So I'm saying your E question marks is defined in a different way, maybe, because all of EI, because you have mentioned all of EI greater than equal to 0.
Yes.
Now, is there E questions mark is also included in this EI?
No, it is not included.
It's not included.
No,
Now,
I is just the numbers of the hypothesis. Now this
exactly.
question mark is different from the others. Yes.
Okay, but you're saying the previous constraint, sum over I EI less than equal to identity, that actually, because your identity minus sum over I EI, that is your E questions marks, and that is greater than 0 is assured from
Yes.
that condition. Okay.
Yes. So this is the greater or equal than 0 for the question mark
Yes,
element.
got it. Okay.
If you have this condition in here, that's why I said that the difference between them is the E question mark element, because if you from here assume that this is, well, it has to be fulfilled, you have it is greater than 0, then because you are solving it, E question mark is greater than 0. But E question mark is something that I told you operationally what it is. Okay.
Yes.
Just this. But in here, it doesn't appear.
Yes.
So we don't need it to construct the semi-definite program, but this is operational.
Yes.
Okay.
Thanks.
And we can substitute it in here and then minimize over the number of outcomes the number of times that we say we don't know. Okay, but this is a operational definition of this element that is actually very real, but we don't need it for the SDP because it's already hidden in this condition.
Okay, thanks.
Okay, so this has one problem that I see here, that Tatagoto is here and he knows that this has some problems, and you can ask him later if you want how does he solve it, and we solve it some other way. But when facing the dual instance of this program, you encounter a problem that I'll define. Here, if you construct the Lagrangian, you have the objective function and the output of the primal, okay? And then you have here the condition that has to be equal to 0, okay? And we are using a slack variable that in here is a real number, okay? And a real and not positive, because you remember that this has to be equal to 0, but it could be this greater, smaller than 0 or greater than 0. Okay, and then that this I'm sorry, that this condition is fulfilled, and now y will be positive. And of course, the positivity of all P of M's. So these are the first constraint, the one corresponding to the trace of outcome different to the hypothesis you have is equal to 0, the one of the semi-completeness relation, and the positivity. If we group up everything with the primal variables, we have these constraints, okay? And then the same output for the dual. So the trace of some operator. Then the dual reads that we are minimizing over all operators y, the trace of y, subject to y is positive, and that this condition is satisfied for all i's. Okay? And this element that we introduce, this variable, nu ij, is real. So the problem with this dual is not that it is complicated, but the problem is that in most of the scenarios that we encounter, these nus go to infinity. Okay? And you need nu to go to infinity in order to fulfill that is positive, because you always have in this sum of operators, you always, at least in the cases I've encountered, you always have a negative eigenvalue. So you need this to go to infinity in order to approach 0. And this is a problem because it complicates a lot the results or the proofs that you can use to prove that your POVM election, your ansatz that you are trying to prove that is the optimal POVM is actually optimal. And I remember that that I also saw was that if you induce an isometry on the hypothesis you have, okay, and you restrict yourself to a smaller scenario, you can relax the condition that this, you can relax this condition, and therefore it's easier to solve the dual problem that you will have, getting rid of, as far as I remember, getting rid of this going to infinity and relaxing a bit the problem to make it easier. Our approach, usually what we do is only for pure state, but we can get rid also of this condition and make the solution easier. So for pure states, we have an object, which is the gram matrix, that contains all the relevant information for a discrimination task. Okay, the gram matrix is defined as the overlap of the unnormalized pure states. So if you have an hypothesis I and hypothesis J with prior probabilities, the gram matrix entry is this one. Okay, and see that is the diagonal elements are just, as I wrote, the prior probabilities. Okay, and this is useful for a lot of things, but the most important one is that when you're trying to work with several qubits, your dimension in principle should be 2 to the n, that can increase or can go to large numbers very easily. But the dimension of the gram matrix is n times n, so you have n square entries. And the dimension of the Hilbert space is much greater. And as I said, the gram matrix contains all the relevant information. So we are reducing already the dimension of the problem a lot and simplifies the things a lot. And this could be useful also for numerical computations, because you are reducing the cost of solving these matrices that we encounter in the SDP. So 2 to the n compared to n, if it is 2, it's 4 equal. But if you have 3, you will have a 3 times 3 matrix, but you will have 2 to the 8, 8 by 8 matrices, which will be very complicated to use in a computer. And see that the gram matrix now can be written as because the gram matrix is positive, can be written as this decomposition. There revision.
Yeah.
Yes, some.
I'm sorry. But those so when you are talking about 2 to the power n cross 2 to the power n elements, so that means that you are then considering the full basis, right? I mean, so
Of course,
it is like
yes.
yeah, but here it depends on how many states do you have in the ensemble. So
Yes.
if you have like for example all of them are different in the sense that they are linearly independent, and but for that to happen, like they need to be of the order of like the basis, no? I mean, so that is not so if you, I mean, if you cannot like discriminate them perfectly, uh, then I mean, for example, for qubits, let's say you can consider like, but if you have to okay, so it is no, for qubit it is not a good example because it is just 2 cross 2 in both cases, I guess.
Well, for example, I have an example. I can go to it a little bit earlier that I wanted, but okay, if you consider this example in which you have several qubits, 2 to the n,
Right,
okay,
right.
and you have one of them different, okay,
Okay.
and this can be in any position of the string, and all the rest are zeros,
Right,
and they are qubits, okay. So you have n possible
yes.
states, okay, but you have 2 to the n Hilbert space.
Possibilities, of course, yeah.
Yes.
Yeah, I mean,
So, but
by
you
2 to
cannot.
the power n, you mean that the
In
ensemble would have been like anything from the, like even the zeros could be 1 or anything else. Like it is
yes,
not only about psi, the position of the psi.
that's it. So when using the gram matrix, you are actually what you are doing is you are changing the representation of these states to the one that they span instead of the one that composes the full Hilbert space. So this is actually what you are doing, and this has a lot of representations that you can use, and one of them is more appropriate than the others. But in here, if you try to use it from the full Hilbert space, is fairly complicated to distinguish which is the basis, let's say, or the states of the basis that you need in order to have your space where your hypothesis live. Okay, when you go to the gram matrix, okay, you are using another representation in order to get rid of these things. Because if you have two ensembles that have the same gram matrix, everything will be the same. The success probability, everything. Okay, is then the transformation to your Hilbert space, your initial Hilbert space, that gives you the actual POVM elements and the measurement you have to perform. But the procedure is the same for the gram matrix. You don't care about the state or the dimension or the Hilbert space they live in. You only care about the information contained here.
Yes. So I mean, that is what, like, for different ensembles may have the same gram matrix.
Yes.
But when you consider that 2 to the power n cross 2 to the power n, that is different for all ensembles, right? I mean, that cannot be same for two different ensembles. I mean, what I'm saying
The
is
what?
that,
Sorry.
I mean, let's say when you are saying that if you have if you consider the Hilbert space dimension, then I mean, then that information will give you the full information about the ensemble. But two different ensembles cannot have I mean, may have the same gram matrix. So what I'm saying is that, of course, gram matrix simplifies your problem in this case, but it definitely does not have all the information about the ensemble.
No, it has not all the
So that is
information
why,
about the sample, but it has all the information relevant for a discrimination task.
exactly. So that
Yes,
is why it is a
because for example,
simplification looking at this problem.
you could have 0 and 1, and this gives you a fairly simple gram matrix. But you could also have plus x and minus x, and this
Yes,
will
yes.
be everything the same, apart from then converting your POVM in your representation to the actual space that you have. So it does not contain all the relevant information of the sample, but all the relevant for the discrimination task.
Right. Mhm.
And you are actually
Yes, sir.
asking, let's say, which is the success probability,
Yes.
or what is the POVM element in relation with your hypothesis.
Okay.
Okay,
Okay, so
Acha, so
And that's fine.
so taking this forward as what Shom is asking, so that means can we say like this, that suppose there are two ensembles who have the same gram matrix, so we can say that if the task is a discrimination task, then those two
Yes.
ensembles are basically the same.
In the discrimination task, yes.
Yes. So, but
So the
they may
success
differ in some.
probability. Tell me.
What I'm saying is that suppose what Shom was asking, that suppose I have two ensembles who have the same gram matrix. So if now my task is a discrimination task, so at using this task, I can say that for this particular task, those two ensembles are actually the same because they have the same gram matrix.
Yes.
But there may be some other task where the two ensembles are different, and that information is not contained in the gram matrix.
For sure.
Am I correct
Yes.
to say this?
Yes. It could be that
Okay.
they are different
Ah.
and you need some other information that is not contained. Yes.
Yes, that is not contained in the gram matrix. So for that, I may need the whole Hilbert-Swiss dimension.
But for discrimination and exclusion and everything of statistical inference, they are equivalent.
Yes,
they have all the relevant information. For some other things, might not.
Might not. Yes. Okay, fine. Thank you.
Iago, sorry.
Yes.
Could you please write this form of this chi k mod square?
Sorry?
Could you please write the form of this xkk, mod of xkk square? Because in case of a minimum error discrimination, it was like a trace of some ei psi I, something like that, right?
Now I'm lost. Sorry. You want
So
this?
what? Yes. What is the form of these things? How it is associated with the earlier representations?
Is just the diagonal elements of this matrix square.
Okay. So
because what we are doing, okay, what we are doing is decomposing our states, okay, in this form. Let's say that x is the sum, or I don't know if it is x or x dagger, is omega times your states. Okay, this might be, yes, this thing. Okay.
so
it's of this form.
Here your psi j or psi I, whatever, this is the ensemble that you want to discriminate, and omega I is the associated with the POVMs or the associated with the projectors that will distinguish, right?
Yes, it is associated. It can be of this form, but see that the choice is not unique. So you could have this is equal also to x u dagger and u x with some unitary, some changes of basis or whatever. So the choice of your POVM element is not unique, so you can maximize over this choice. And if you do, let's say, sorry, with I square, this is the probability of saying I when it was I. So this is your success probability.
Exactly.
And this is why we are saying that the success probability, sorry, of with this description of the ensemble or the gram matrix, sorry, is this one, the sum over k of the diagonal elements squared. Right?
Yes, correct.
Therefore, the the optimal solution is just maximizing over X. But this is not, this is quadratic, so this is not an SDP. Okay, this is an optimization problem that it could be solved, but this is not SDP. That's why I didn't mark everything in colors. But with this formulation, actually, what we can do is, okay, let's say that we impose the condition of the trace of the hypothesis with the POVM element is equal to 0, and we call it a projector and normalize. Okay, given that the trace, sorry, the overlap between the hypothesis and some other the projector of the measurement is equal to 1 if they are the same, or 0 if they are different, which is what we want. Then the success probability is not equal to 1 always, because we have this this number, this scalar here, and it's given by the sum of these scalars. Okay, and we need also that the question mark element, the I don't know answer, is positive. Okay, and now we can write the SDP in a easier form. Okay, we have the maximization over all possible elements, POVM elements of this form that we had before. Okay, subject to this is equal to 0, but this is already imposed by construction, and that this, sorry, it's not now, that these elements are positive, okay, in order to the POVM elements as they are projectors of this form, and then with a scalar this has to be positive, and that this sum is less or equal than the identity. Okay, and here we have that you multiply, in order to simplify it more, you multiply by X dagger here and by X, and X was the gram matrix, so this identity will convert to the gram matrix. Okay, and each of the elements will be delta if they are the same. Okay, and if not, well, 1 if they are the same, or 0 if they are not, then we will have a matrix that will be by gamma 1, gamma 2, 3, and we call it gamma diagonal. Okay, then this condition is just that this is positive, and we are maximizing over one operator only. And this is easier, and this is solvable. Because if we go to the example I told you before, which is something we've done in the past, consider that the ensemble has equal prior probabilities, 1 over n, for every n, for every hypothesis, sorry, and consider also that the source is symmetric in this special way, that 2 hypotheses have overlap C, or let's say C square, okay, because you can say other state that this is of this form, okay, so you will have this one with 0 is equal to C, and this other that I have is equal to C, so you have C squared, let's say. Okay, but it's symmetric in this special case. And this is something that is anomaly detection. Like you have allegedly a source that prepares states in a given state, let's say 0, but some of the machines that you have, it's twisted and produces by chance another state that you don't want, and you want to identify which one of the machines is broken or twisted in order to fix it. So in this scenario, all condition probabilities, because the source is symmetric, is equal. And this simplifies a lot the SDP, because it's just the maximization over one scalar, subject to this scalar is positive, and that the identity times this scalar is less or equal than G. And this, as we saw last week, this is the SDP only for the smallest eigenvalue of a gram matrix. I think we saw the largest eigenvalue, but this formulation gives you the smallest. Okay, and this is easy to solve because you have the gram matrix. It's already defined, the gram matrix, so you only have to diagonalize it, which is not trivial sometimes, but you can. Okay. Yeah. Last thing I wanted to mention is just of a couple of 2 more slides, which is quantum state exclusion. And in here, the problem or the task you are dealing is, let's say, the opposite of the other one, of the state discrimination. Instead of identifying which of the states you have, you are excluding one of those that you have. Okay, imagine that I have before, as we of all a bunch of zeros, and at some point I have a different phi state. Okay, I can say it's not in the first one, it's not in the second one. This might be useful for, instead of actually identifying where the state is, which is demanding, what is not, and use these machines, for example, to continue the production until you discover which is the machine that is failing. So in here, you have an ensemble, and you grab some unknown state, you measure, you have an outcome, and your decision will be, okay, it's not this one. Before it was, okay, I know that it's this one. Now I'm sure that it will not be this hypothesis. Or in the case of anomaly, this machine. And here, instead of instead of doing the maximization over the POVM elements, you are minimizing the outcome of the trace of given an hypothesis I, you obtain the outcome I. Because this outcome now represents that it's not rho I. So you want to minimize this probability. And the constraints are all the same. You have that they have the completeness relation, and you have that is positive. Okay. Another formulation is the maximization over the rest. Okay. Which will be the success probability in this case. For j different than I, you are maximizing the trace of the outcome j for the hypothesis I. And again, the completeness relation and the positivity. Okay. But this is the same problem as before, but with the minimization and the maximization swapped. Okay. And this was, let's say, the minimum error protocol or identification or discrimination, but here for exclusion. And you could have also the unambiguous or zero error state exclusion. You have to maximize the success of them being different. But in here, notice that I didn't put that j is different than 0 because I'm imposing that they have to be 0 because this is the 0 error. When I exclude one hypothesis, I'm 100% sure that it was not this one. Okay, and again the same, that this is less or equal than the identity, semi-completeness relation, and that they are positive, each of the POVM elements. And I don't know if I have something more. Yes. To finish, I will mention that if you read this book, it's fairly good. It goes straight to the point, and it gives you a lot of example, not in too much detail, but it gives you a lot of example on why SDP is important in quantum information. It gives you a bunch of topics that they work with semi-definite programming. And yeah, so if you want to take a look to this book, it's probably okay. Some others that I can recommend is the lecture notes of Batros, Semi-Definite Programming by Batros. There are lecture notes that are available online. And if I'm not wrong, the Boyd and Vandenberg book also. Okay, so that was all. I don't know if you have any questions.
Santiago. So you said that for the state exclusion, can you go back to the state exclusion slide?
Which one, the unambiguous or minimum?
The minimum error.
Okay.
So here you are saying that it is the same thing like the state discrimination SDP, but the minimum and maximum is now dual. Yeah, swapped. So in that case, I mean, is it guaranteed that here also you will get a solution if you have obtained some solution for the for the discrimination task? Like, is there? I mean,
yes, and it will be greater also. Okay, because when you are trying to identify exactly which one it is, okay, you have the same success probability if you identify and then say randomly it was not this other one.
Okay. Yes. Okay.
So operationally, you have this intuition that it will be greater. But you can do it. In here, you have that this is the error probability, but you can interpret it as it is the worst possible measurement in some sense.
Okay.
So distinguishing, so the success probability when you are performing the worst you can is fairly high. So this is the intuition behind it. I don't know if mathematically it's sure, but if you have a solution for a discrimination task with the same ensemble, at least the success probability of excluding something is higher.
Yeah, of course. Yeah.
And if you exclude randomly, okay, you have n minus 1 over n. So it's fairly high.
Yeah. Okay.
So for every minimum error problem, it doesn't matter if it is straight discrimination or exclusion, you always have a solution which is peak random. Okay, so your success probability is greater than 1 over n, or the sum of the prior probabilities. And this is the choice of the element that AI is equal to I over n.
Okay. Yes. So this is the worst possible measurement, of course. Yeah. And also, in worst case, you have the same problem as discrimination. You have to again bring it to the SDP form through the gram matrix and things like that.
Yeah, at least for an ambiguous quantum state exclusion, for the zero error, we want to convert it into the gram matrix problem because it reduces the complexity of the problem. But there are some other instances in which we are working that for the minimum error is also appropriate to work with the gram matrix because it has, let's say you have more tools to work with rather than SDP. SDP gives you a lot of information and it helps you to find the optimal solution, but you can work with some other things.
So that gram matrix can give you the optimal success probability value or something like that, but it does not give you optimal measurement setting. No, I mean it does not give you. Does it give you the actual projectors or like actual elements of the POVM? No,
not directly. But it depends on some cases. For example, if all the diagonal elements of the square root matrix of the gram all the diagonal elements are equal, it gives you the POVM. But not in all the cases. You have to find it. But you can find it from the gram matrix.
Yeah, so that is what I'm saying. Now that is another motivation matrices.
Using the decomposition, okay, and you can write it in terms of the hypothesis you have. But
Right. Yeah. Okay. Thanks.
okay.
Yeah, I just so that means I have to just find out this x dagger x and find its eigenvectors, and those eigenvectors should be associated with the required measurement, right?
Yes.
Okay.
But the eigenvalues, eigenvectors, sorry, for the x, they are related.
Yes.
In this sense, and they can give you the if you use the correct representation, they can give you the success probability and the POBM elements directly, but not from the gram matrix. If you compute the gram matrix and compute the eigenvectors, it does not directly convert into your measurement. You have to work a little bit harder there.
Okay. Oh, I see. Okay. Okay. Because all of these psi I are not orthogonal with each other. So, okay. I got
Yes, that's it. The ones that are orthogonal are these omega I.
Yes.
Because they form
that is the spectral
a
decomposition.
basis, at least for the
exactly
for the minimum error.
Yes. Okay. Thanks. Thanks for the nice talk.
Thank you.
Okay, if there is no more question, let's thank Iago again, and really it's a very nice talk for beginner like us, and thank you.
Thank you.
So goodbye.
Thanks. Thanks for the nice talk, Iago.
Thank you.
Yeah, thanks, Iago. So you have prepared it in a very small time scale, and
yeah. So Iago, just one more thing. Can you share this file with us? Yesterday, the last week files and this file.
Yeah, it's all in the same file, so I can clean it from
yes,
the
it would be
things that
better
I wrote. But sorry, I cannot hear you.
Sundar, can you mute yourself, please? Sundar? Yeah. So Iago, one more thing. It would be better if you, because you talked about some references and some of the reference also you mentioned, but
yes.
Okay. Lastly, you talked about some references, some lecture notes that is not mentioned here, I think. So it would be better if you could write it down. That what are those references?
I think I wrote them.
Oh, I see.
But I can group everything up and send it a little bit more clear. But yes, are these notes. But in any case, I wrote them together and I will send all the references. But these are the lecture notes, the outros from a lecture series that we gave that are available online. But I will send everything together with the file. Okay, all the references listed properly.
Okay, that would be great. Thanks.
Okay, no problem. Well, that's it, right?
Yes. Yeah. Thank you very much.
Okay. Thank you. Thank you, guys.
Okay. Bye.
Bye. See you.